right, in this video we're going to talk about how to pool the variance or the estimated population variance when computing an independent group's t-test. So let's talk about the mechanics of the independent group's t-test to start with. In the t-test, an independent variable is going to be manipulated, and there's going to be two levels of the independent variable. Now, subjects are going to be assigned to one of two conditions that correspond to the different levels of the independent variable. And generally speaking, it's good to kind of learn these concepts in the context of an example. So in this video, I'm not actually going to throw any numbers at you or anything like that, but I want you to really focus on this whole concept of why we pool together variance estimates from our two samples. So in our example, we're going to ask the question, can communication training increase the quality of marital relationships? And this actually is based on some research I did with Ed Cabaney back in 1995 and some other colleagues. And that paper that was published is called Impact of Labeled Anger and Blame in Intimate Relationships. And really what it comes down to is, how do people express themselves? Because the words that they use are important. And what we were interested in was if people kind of own their own feelings rather than blaming their partner, would that lead to enhanced marital communication? And something as simple as saying I rather than you when discussing a contentious issue, or using distress words rather than anger words when communicating how they are feeling. Would that have an effect in terms of how their partner perceived the quality of the overall communication? So is it the case that using I words and distress words facilitated better quality communication, especially in troubled couples? So let's talk about a hypothetical experiment we could run based on that. And we'll have participants be men and women who come from troubled relationships, but only one of them will actually be involved in the experimental manipulation. You'll see why in a moment. And so the independent variable might be a short interactive online instruction in communication training, right? Teaching people to use I words and distress words rather than anger words or saying you. Okay, so that's the communication training. And they'll be compared to a control group that has no training at all, never goes through the online instruction. So we have two samples, right? Two groups. Okay, so the dependent variables, we can measure outcome in this any of a number of ways. For example, we could count the number of I words used and distress words used when our experimental subjects engage in a 5-minute discussion on a troubling topic with their partner. And we would expect that if they've had the training, they would be more likely to use I words and distress words. We could also, as a dependent variable, measure partner ratings and the overall quality of communication. And of course, we could probably go on with other potential dependent variables as well. Okay, now what we're going to have to do when we run the statistical analysis is estimate the population variance. Just like we did with one sample t-test, we need some estimate of the population variance because most of the time we do not know the population variance. So we get our sample data and then we estimate population variance from the sample data. Now the trick here is that we have two samples, right? So if I were to go through just a flow sheet of what's happening in this hypothetical experiment, probably had random assignment of individuals to the two different conditions. And in sample one, individuals completed the video training, and of course we could calculate estimated population variance from that sample for group one. And we could do the same for the second sample, the second group. And let's say that that's the control group that receives no training at all. We could create an estimate of population variance from that group. So now we have two population variance estimates. Right, the experimental group then gets the manipulation of the independent variable, completing the training, and then both groups will complete measures of the dependent variable. Now, the measures that they complete are actually called the dependent measures, but the measures are essentially measuring the dependent variable in some way. So what we're looking for here is the effect that manipulation of the independent variable, right? It has two levels. Either you completed the video training or not, right? The effect that that has on these scores down here on the dependent variable. So we have two groups of subjects, and if we create estimates, Let me get rid of that little arrow right there. I'll take these off. And if you have estimates of variance for each group, then the question becomes, well, which estimate should we use, right? We've got two variance estimates. So one of them is right here, and the other one is right here. So those are estimates of population variance from samples. Which one should we prefer, right? And there's really no logical reason to prefer either one of those. So what's our answer? Our answer is to pool those estimates together, right? And you might say, well, why not just take the group that has the largest sample size, because we know as degrees of freedom increases, so should the standard error should decrease, right? We get better estimates of the population variance. Well, if we do that, we're really not using a lot of data, right? Because all of the data from the other sample, the smaller sample, wouldn't be included in our variance estimate. So that's a pretty inefficient way to go. So what we're going to do, again, is assume that the variances in the population between these two populations represented by the samples, we're going to assume that those are equal. That's the homogeneity of variance assumption. And then we're just going to pool the variances. Now, when we actually run the t-test, we'll test that assumption. It's called Levine's test. We're going to test whether or not that assumption is a good idea. But we're going to assume for now that they're equal in the population. And then that will allow us to do is then pool the variance estimates from our samples. So we need a formula for how to do that, right? So by pooling the variance, we get a weighted average estimate of the population variance. Right? And we need that. Now, why do we need that? Well, because for the t-ratio, if you recall, we have to have standard error in the denominator. So we have to have some measure of how much error we expect in the sampling distribution and really what that looks like. Now, this is going to be the next topic of discussion in the next video, and that is that pooling the variance, which is what we're doing now, is the first step in a two-step process to compute what's called the standard error of the difference between independent means. That's a mouthful. Okay, so in our one sample t-test, we computed something called the estimated standard error of the mean. Okay, we're going to do something akin to that, but it's a little different and it needs more explanation. And that's called the standard error of the difference between independent means. So it plays pretty much the equivalent role of the estimated standard error of the mean in the one sample t-test, but it's going to require some more elaboration. And like I said, that's going to be more fully defined in the next video. So for now, we're just going to focus on this first step. Let's pool the estimated variances that are drawn from each sample. And again, I'm not going to go through any math right now, but we will go through an example later. Okay, so how to pool those estimated variances, and you'll look at this formula and say, wow, that's beginning to look a little complicated. I'm not quite sure what that means. Well, let's just walk through it. It's actually pretty simple. Okay, this first term right here is the estimated pooled variance. And you'll notice that there's a P down here, right? And sometimes in textbooks it'll say pooled, but you can just shorthand that and put P, it means the same thing. Okay, so that's our term. What we're trying to solve for now is the estimated pooled variances, where we're getting the variance estimates from each sample and pooling them together. So the first thing we put in the numerator then is degrees of freedom for group 1, and then we multiply that by the population variance estimate for group 1 as well. Now, depending on the textbook you're working with, and I think I've said this a couple of times in other videos, depending on the textbook you're working with, sometimes the pooled variance estimate is reflected like this, okay, and that's the textbook that we use in the class that I teach. But other times you'll see it like this, sigma, okay? And so that's not a very good sigma, but you know what I'm trying to get at, right? So they mean the same thing. So just take that into account as you're thinking about these terms and what they mean, okay? Both of them mean estimated population variance. They're just expressed a little bit differently. But anyways, so in the numerator, we have the estimated population variance for group 1 multiplied by degrees of freedom. And then we do the same thing for the second group. okay? And then in the denominator, we have the total number of subjects in the experiment minus 2. And the formula for that is simply to take degrees of freedom for group 1, degrees of freedom for group 2, and then add them together. So that gives you degrees of freedom total. But for an independent groups 2 test, because you have 2 population variance estimates, you have to subtract a degree of freedom for each of those estimates. Okay, so we need to pool the variance estimates in order to calculate a meaningful form of standard error. And one thing to note is that this formula creates a weighted average. In other words, by including degrees of freedom in the numerator, it takes into account sample size. And as we mentioned in a previous slide, bigger samples tend to be better estimates of population parameters. So that's why we want to weight it. Okay, so then what's the next step? Well, the next step is we have to create a meaningful estimate of standard error. Okay, we've now pooled the variance estimates. Now we actually have to create an estimate of standard error, and it's worth looking back on the one sample t-test as we try to understand this. If you recall, in the one sample t-test, okay, the numerator was simply a difference between the means, right? We subtracted out the population mean from a sample mean. So what that means is the denominator had to represent some estimate of the standard error, right? So it's the estimated standard error of the mean that we put into the denominator. And what that really represented was how much we expect sample means to differ from the population mean on average in the sampling distribution. Okay, and that's how we got the t ratio. So what we're going to need to do then is create something for an independent groups t-test that puts an equivalent term in the denominator. That's an estimate of standard error. And for an independent groups t-test, we need to have a meaningful estimate of what that standard error represents, because conceptually it's a little different than what we thought about with a one sample t-test. But that'll be coming in the next video. Okay, so big picture, there is no logical reason to prefer one sample's estimated population variance over the other sample's estimated population variance. As a result, we are going to pool the estimated population variance from both samples. The formula for that pooled estimate takes into account the size of each sample by including degrees of freedom in the numerator. We want to do that, right, because larger samples are better estimates of population parameters. So by including degrees of freedom in the numerator, we get the best possible pooled estimate of the population variance. And the point of doing all this is that pooling the variance is the first step in calculating a meaningful form of standard error for the t ratio when you're doing an independent groups t-test, sometimes also called independent samples t-test. Okay, so our next video is going to talk about how to create actually the standard error once we've pooled the variance. And we're going to be using the same research example in that, so we'll do that next. And then we'll actually run the numbers. We'll create some hypothetical data and run the numbers and actually calculate the t-test. For now, though, let's just focus on the concepts, okay? Let's focus on what we need to be doing, looking at the formulas and so forth. So I'll see you in the next video.